Namaste. Namaste everyone. Welcome to Dual Nature of Light classes, physics classes. In the last class we have studied about that experiment by Hallwalk and Leonard by taking ultraviolet light and making it to fall on a photosensitive plate. We have seen that, and that was a very important and major experiment. And today we will continue that experiment. What did they do? Finally, what conclusions they have got? Namaste. Namaste everyone. Welcome to the photoelectric effect class. Right. So again, take a piece of paper and try to write the diagram along with me. And it is not me who will get benefited with this class. It is you who should get benefited. Right. So you take a piece of paper and start drawing the diagram. That diagram is very important. Okay, some people minimize it and draw without any commutator and all, but it is a risky job that may fetch you mark in the examination, but still better you draw the full diagram. It is very easy actually. So how is the diagram? You should take an evacuated chamber, right? Because emitted electrons must freely move inside the chamber. So this is an evacuated tube. There is no gas inside. Some people fill it with a small amount of inert gas so that you will get enhanced current, because when the electrons flow through that low pressure gas, they collide with the gas molecules and release few more electrons. So you will get a noticeable current. But here we will take it as evacuated chamber, and which is the best suitable radiation which can remove electrons from the surface of a metal. You know, it is ultraviolet, which is certain wavelengths of ultraviolet are less harmful to the human being, and they are more energetic than our visible light. Okay, so this should be what type of window? It should be quartz window, because if ordinary light is used, okay, then it is glass window is okay. But since we are using ultraviolet light, it should be quartz window. Otherwise, ultraviolet is completely absorbed by glass. So it should be quartz window. So this is the source, and okay, this is ultraviolet light is made to fall on the photosensitive cathode. Cathode should be given negative, because once the electrons are they are coming out, they should not reach back to the cathode. They should move and produce the current. And here is an anode which is ready to accept these electrons, and they should be connected, right? So while connecting, you should have commutator key first. See the way in which I am drawing it. First the commutator key, and you interchange it and connect it like this here. So here it should be jumped off and connect it here. Okay, yes. Then connect these two and jump over here the corners. Then from the middle one you have to connect it to that accelerator, the potential difference battery. So you should be ready with a very long wire with a resistance, or a rheostat, you can call it as a rheostat, which can change the current, and you connect it to a high tension battery like this, plus minus like this. And when this is connected here, and this should be connected here, wherever you want, you can change this. And here should be a current recorder, that is ammeter, microammeter, very sensitive microammeter, which can record current of very small order also, right? And then whatever the voltage that you apply can be measured using a voltmeter here, from positive to the positive of the voltmeter, from negative to negative, from negative, positive, like this, right? Now, how is the experiment done? That's over, very simple. So you have to write commutator here, commutator. And what else you can write? This is voltmeter, ammeter, it is written already. It is enough, I think. This is evacuated chamber, evacuated tube, or vacuum tube. And electrons we have not shown. Very important persons in this, right? Without showing electrons, no photoelectric effect. Yes. So Leonard and Hallwalk, they did the experiment with different varieties of, with the different trials and errors. They tried different ideas. One thing is changing the intensity of light. Taking the same color light, taking the same wavelength light, same frequency, but brightness more. What is the argument of Einstein and this Max Planck when intensity is more? You are making more number of similar photons. less number of similar photons means it's a less brighter light. Same type of photons, more in number per second, means it's a brighter light. So the difference between 100 watt sodium lamp and 100 watt sodium lamp and 40 watt sodium lamp is 100 watt sodium lamp and 40 watt sodium lamp. Difference is 100 watt sodium lamp is more brighter and this is less brighter. Both are emitting same h nu. There is no difference in h nu, but more in number, more photons per second. Here less photons per second. That is the difference. That's why 40 watt lamp is less brighter. Whereas if you have 100 watt sodium and 100 watt mercury lamp, right? Mercury lamp is you have seen in street lights. 100 watt, both 100 watt, same number of photons same, photons per second may be same, but h nu 1 is different from h nu 2. Energy of each photon is different because you have changed frequency. So you can change the frequency of the source, wavelength of the source, and you know energy E is equal to h nu, which is equal to hc by lambda. As you decrease the wavelength, as you move from visible, ultraviolet, X-ray and gamma rays, you are moving towards lower and lower wavelength radiation, and you are getting more and more energy, but frequency is increasing, right? Wavelength is decreasing as you move from visible, ultraviolet, X-rays, gamma rays. Gamma rays are much stronger, lesser wavelength. Energy is inversely proportional to wavelength, energy is directly proportional to frequency. This should be at the tip of your tongue, and there shouldn't be second thought when it is asked. How if frequency is increased, what happens to the energy of a radiation? Keeps on increasing. If the wavelength is decreased, energy increases. If the wavelength is increased, energy decreases. If the wavelength is decreased, energy increases. Okay, so they did the experiment by, I rub this because this should be kept in mind. Yeah, by doing so many things. First one is they increased the brightness. When the intensity of incident light is increased, suddenly they came to know that photoelectric current went on increasing. More and more current they got. And so, so brightness or intensity of incident light, intensity of incident radiation is directly proportional to photoelectric current. This is one conclusion they brought from this, and it has not changed the kinetic energy of the moving particles. And they draw a graph of, when you draw a graph of intensity versus current, photoelectric current, and versus intensity of incident light, they got a straight line. When there is no intensity, what do you mean by no intensity? Bulb is switched off, that's all. No photoelectrons, no current. When the brightness is increased little by little, then the photoelectric current went on increasing. Remember, this experiment has to be done with those photons which are capable of removing electrons, right? For all frequencies, for nu greater than nu naught. Only those frequencies, only those photons which can remove electrons. With those photons, if you try this, brightness more, brightness less, you can observe this. If those photons cannot remove electrons, itself means no question of changing intensity. There is no meaning of changing in intensity. So, for all frequencies greater than nu naught. What is nu naught? Nu naught is called threshold frequency. Hope you can see if I write it here. Nu naught is a threshold frequency. What do you mean by threshold frequency? It is the minimum frequency above which photoelectrons are emitted, and it is the frequency below which photoelectrons are not emitted, right? So minimum frequency above which photoelectrons are emitted, the frequency below which no photoelectric emission takes place, that is called threshold frequency. So if you want to do something with the photoelectric effect, your threshold frequency, the frequency of incident radiation must be more than threshold frequency so that it can emit photoelectric effect. So what is work function? It is the energy required to remove the electron, minimum energy. So can you get this work function from threshold frequency? Definitely. because threshold frequency is that just minimum frequency which can remove electron, and convert it into energy, h nu naught. That should be the work function phi naught or phi, whatever it is. Okay, so we have the minimum frequency which can remove the electron, that is threshold frequency, convert it into energy h nu naught, that is work function, minimum energy required to remove the electron, and we have the intensity directly proportional to photoelectric current. Now coming to another part of the photoelectrons, kinetic energy. How fast these electrons are moving. For that, what you have to do, you have to interchange. See here now how the cathode and anode are connected. If the switches are given here, again the same thing, but I want to repeat it so that it enters into your brain clearly. So if this is connected, what happens? Here, cathode, connected, 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 negative. Cathode is connected to negative. Anode, here connected. If you go by this way, no use. Open on both the sides. So here connected, positive. Anode will call the electrons, come here, negative charges, I am positive, come. What about cathode? Will repel them. Once the electrons come out of the material is not ready to receive it. Electrons come here and they join with the anode and complete the path, and you get current. Now, how to measure the kinetic energy of all these electrons? Stop them. How much energy is required to stop them completely? That is the energy of the kinetic energy of the electrons. How to stop them? Reverse the connection. So now we are coming to the track, what we have stopped in the previous class, right? I think we have discussed this also. So reverse it. What we have to reverse? Commutator has to be reversed. You know that this is commutator now, so I will reduce the number of letters here. Yes, connect it here. Now see, cathode. Cathode is connected here, positive. Yes. What about anode? Anode should be given a positive, but now it is given negative. Anode negative. Now let us start changing this one. If you put an arrow mark like this, it does mean that you are changing the battery, changing the value of voltage in the battery. Now let us start from this reverse potential V. 0 volt. The negative given voltage is 0. Whether you get photoelectric current 0, whether the electrons reach the anode, of course photoelectric emission definitely takes place, because we are making the radiation to fall on the cathode, and the cathode is receiving the photons, it is emitting electrons, everything is happening. There is no problem for photoelectric effect, but the emitted electrons, they come out. They have sufficient energy. You have taken how much money? You have taken 150 rupees from your father. Only 80 rupees for your journey. 70 rupees is left with. So the electrons are running now. As they run, there is the anode. But anode says, I am negative, don't come, I am repelling you. But electron says, we have enough amount of energy, who are you just repelling us? Please go aside. So they move with their own energy, overcome the repelling force and reach here, produce the current. But current will decrease because some of the electrons may not be able to reach. Make this minus 1 volt. That means just simply increase it, that's all. Minus we have done already by changing the connections of the commutator. When it is made minus 1 volt, some of the electrons in the running race may not be able to reach the anode. So when they don't reach the anode, the amount of current goes on reducing. But anode may not be successful in stopping all the electrons, because that minus 1 volt may not be enough to repel all the electrons. So what happens? Photoelectric current decreases, make it minus 2 volt, photoelectric current decreases, but there may be still few more electrons which are more energetic to reach the anode, and they may reach, but still their number is less. Current decreases, because current means rate of flow of charges, number of electrons flowing per second. So when the more number of electrons reaching the anode becomes lesser and lesser, definitely the photoelectric current decreases. Make it minus 3 volt, decreases, minus 4 volt. Now the photoelectric current becomes 0. Say, then this potential is called stopping potential. So what is stopping potential? Stopping potential is the minimum negative potential. Sir, if I make it minus 5 volt, will the electron stop? However, if you can stop a bicycle means, why can't you stop? If you can stop an elephant means, why can't you stop a dog? You can definitely do that. So if minus 4 volt can stop all the electrons means, why can't minus 5? It can do it, right? So if you can stop an elephant means, you can stop a dog also, no problem. And so stopping potential is the minimum reverse potential of the anode. Anode is given negative, actually should have been given positive. The minimum reverse potential of the anode at which photoelectric current becomes zero, at which no photoelectric emission takes place. It is not the answer, because photoelectric emission is happening, but the thing is electrons are stopped by the negative anode. So the minimum reverse potential of the anode at which photoelectric current becomes zero is called stopping potential. Now, how do you convert this stopping potential into kinetic energy? Of course, minus 4 volt was able to stop the electrons. But is minus 4 itself is it the energy? No. You know, I was explaining it in the last class. Still, we have not come to this new point, isn't it? But let it be. When in the last class I was explaining about that part. When you have a battery connected to a resistor or a bulb like this, battery will do the work in sending the electrons, right? So potential difference of any battery is the work done in taking the charges, right? So what is the work done? Charge into potential difference. So if you purchase a 1.5 volt battery, what do you mean by 1.5 volt? It is the work done in taking the some 1 coulomb of charge, say, once round the circuit. That is the potential difference. So if you want to know what is the work done by the battery, it is charge into potential. What is the work done by this battery in stopping the electrons? Work done is equal to charge is the charge of the electrons, and potential difference is this V0. I'll call it as V0, stopping potential. It may be any value. Minus 4 is a numerical I have given, but it may not be the same in all cases. We will symbolize it as V0. So EV0 is the work done, and this is the kinetic energy. How much energy was bicycle having? How much work you have done in stopping it? How much energy was football having? How much work you have done in stopping it? One and the same. So work done by the battery is the kinetic energy of the charged particles, EV0. So stopping potential gives the kinetic energy of the it gives, in the sense it can be converted into kinetic energy of the moving electrons. Okay, we have got the kinetic energy. Now Hallward and Leonard did some experiments and some changes to find out the kinetic energy. Surprisingly, they came to know that when intensity of incident light is increased, photoelectric current increased linearly, but there was no change in the kinetic energy. No change in the kinetic energy was found when intensity of incident light is increased. But when the frequency of incident light is increased, remember, if you are given 150 rupees, if your friend is given 150 rupees, friend C is given 150 rupees, everybody is given 150 rupees, you go home, go to grandma's house, right? Grandma's house, spend 80 rupees for traveling. 70 rupees is left with. What is that 70? It is the same in all the pockets. All your friends' pockets, amount of money remaining is 70 rupees. It may not change. The meaning is kinetic energy does not depend on the intensity of light. It depends on the frequency. Suppose you are given 200 rupees, you will be left with 120 rupees. And if you are given 200 rupees, you will be left with the how much? 200 rupees means 120 rupees. 300 rupees if you are given 220 rupees, because 80 rupees for traveling. No, 70 rupees for traveling, right? 80 rupees remain, something like that. Okay. More the amount of money that you are given with, more the energy that you have, more the remaining money. So more the frequency of incident light, more is the energy with photons. And these photons will remove electrons with more energy. When the electrons come out with more energy, they will have more kinetic energy remaining. And if you want to stop them now, you need more negative potential. Is it not so? That means stopping potential depends on what? It depends on the incident frequency, which decides the energy of the incident light, which decides the remaining energy for the electron, because energy to come out is constant. So if I can write it here, right? If I can write it here, stopping potential depends on frequency of incident light, frequency of incident radiation. Frequency of incident radiation decides the kinetic energy of emitted electrons, remaining money, and that in turn decides the stopping potential. But it has nothing to do with photoelectric current. It has no relation with the photoelectric current. You see the beauty? Photoelectric current is decided by the brightness, intensity of incident light. But intensity of incident light doesn't change the kinetic energy of photoelectrons. Because brightness cannot change the kinetic energy. Brightness increasing means you are increasing the photons. You are not increasing the energy, only number of photons. Same type of photons, but more number. What is the use? Each photon should have more energy. Then only you will get more kinetic energy electron. Then you need more stopping potential, more kinetic energy. So this relation is very, very important. What are related now? So shall I write it here? What are related now? One another. The relation is between frequency of incident light, which increases the energy, h nu, energy of the incident light, and which increases the kinetic energy of the emitted electrons. Because if you have more money, you will spend only 80 rupees for your journey or 70 rupees for your journey. Remaining money will go on increasing, and that depends on the stopping potential. But no brightness, no intensity, no current comes into this picture. Whereas if the intensity of incident light is increased, that increases more number of photons, that increases the more number of electrons, that increases the photoelectric current. And here frequency doesn't come into picture at all. Here intensity doesn't come into picture at all. This idea must be very clear. If you have any doubts in your brain, just post a message to me, I will clear it out, because I don't know in what way you are thinking, right? So intensity of incident light increases the photoelectric current, and the frequency of incident light increases the kinetic energy of photoelectrons, in turn the stopping potential. Now we will draw some very peculiar graphs. That is the main thing in this class. Very, very peculiar graphs. What type of graphs? See here. I want to draw, okay, one is photoelectric current versus intensity. More the brightness, more will be the photoelectric current. Okay, I will draw the kinetic energy of photoelectrons versus frequency of incident light. Hope you can see this, right? Kinetic energy of photoelectrons versus frequency. You know that more the frequency of incident light, I will change the frequency. I will change from infrared to visible. And in visible light, I will start from red, then I will take yellow, orange, and I will come to blue. And from blue to ultraviolet, ultraviolet to X-ray, X-ray to gamma ray. That means I am changing the frequency itself. I am going for lower and lower wavelength. I am increasing the frequency. That means I am testing with more and more energetic rays. What happens? Kinetic energy goes on increasing. But I must remember that there is a frequency below which there is no photoelectric emission takes place, isn't it? There is a minimum frequency. If I try for 2.2 into 10 to the power 14 Hertz, I don't get 2.3 into 10 to the power 14 Hertz. I don't get 2.4 into 10 to the power 14 Hertz. I get photoelectrons. 2.5, I get photoelectrons. But their energy is more, kinetic energy is more. 2.6, again kinetic energy is more. But up to this I don't get. This is called threshold frequency, the minimum frequency at which photoelectric emission takes place. But once you cross that minimum frequency, right? If you, suppose today I don't remember how much I told, the bus fare is say 70 rupees, right? Your father gives 50 rupees. You don't go. You don't go to grandma's house, because in 50 rupees you can't travel completely. Remaining walking, that is impossible for me, because I don't have any walking habit, isn't it? Usually people don't walk now. So for 50 rupees you don't start the journey, 30 rupees you don't start the journey, 60 rupees you don't start the journey. When it is 70 rupees, just enough to reach grandma's house, you start the journey. 75, you are happy. 80, happy. 100, you are more happy, you will start the journey. That means the kinetic energy of the electrons, you can see the electrons coming out of the material just when you are incidenting the threshold frequency. When the incident frequency is just nu naught, you can see some electrons just coming out of the material, but they will not have any remaining energy. When you are given only 70 rupees, your friend can see you getting down the bus in grandma's town, right? Or grandma's, near the grandma's house. You are getting down from the bus, but you will not have any money remaining in your pocket because you have given all the money to your bus fare, so nothing is remaining. So you will have electrons just coming out. That is why it is called work function, right? H nu naught is called work function. Now where do you draw that graph? So for low frequencies you don't get electrons at all. At just one frequency you get, I call it as nu naught. What is the kinetic energy of the electrons now? It is 0. Can you follow this graph? When the frequency is less than nu naught, no electrons come out. When the frequency is just nu naught, electrons just come out. They don't have any kinetic energy. But once you go beyond nu naught, for higher frequencies, electrons will have kinetic energy. Can you find it out like this? So this is the graph of kinetic energy versus frequency. But remember, graph doesn't start from 0 as if it was here. If the frequency is greater than nu naught and if the brightness is 0, no current. If the brightness is increased, the electrons come out and you will get more and more photons, more and more electrons. And here, once the frequency is just threshold frequency, electrons just come. But if the frequency is more than threshold frequency, you will have more kinetic energy. If again the frequency is much more, you will have more kinetic energy. This is the graph which is starting from some threshold frequency. So kinetic energy versus frequency graph is a straight line, but it will start from an x-axis. It will have an x-intercept, and that x-intercept is the threshold frequency. Now if I extrapolate this graph, can you tell me what is this? Where kinetic energy is negative, this is nothing but work function of the material, phi. If you take this magnitude wise, it is the work function of the material. Sir, why do you call it as work function? It is the energy just to remove the electron here. Just kinetic energy 0. Just let it come out. Let it not have any energy, no problem. Let it come out of the material. That is work function. So this is negative energy. Electrons are bound inside the material. They can't come out. Somebody must supply the energy from outside so that they will absorb it and just come out. You don't have any money with you, and you are bound inside your house. Your father must give at least 70 rupees so as to reach your grandma's house. So that is just reached, and any energy greater than this is obtained for frequencies more than threshold frequency. So this is the graph of threshold frequency versus kinetic energy. And this is for one metal A. Suppose you draw this for another metal. So I will take one metal where electrons can easily come out. So you test with different frequencies. For some lesser frequency itself, it starts coming out because work function is less. Energy required to remove the electron is less. So you will start your journey from here. Take another metal where electrons are more bound inside the material. They require more energy to come out. That means you have to supply a stronger energetic radiation. That means its frequency should be more. That means its graph will start from here. Okay, or I will draw it from. This is for metal B, whose work function is more, threshold frequency is more, and its y-intercept is somewhere here because its work function is more, right? So it starts from here. So graph should be like this. So if you are given graph like this, see which has more threshold frequency. One which has got more threshold frequency should have more work function. One which has got less threshold frequency should have less work function. That's all. So that is one graph. But graph is not over. We have drawn only two graphs. One is intensity versus current, straight line graph starting from 0. Another is frequency versus kinetic energy. Right? Hope you have followed this one, right? At one frequency it starts its journey, and after that you get kinetic energy, positive. but here it is just an extrapolation. Negative kinetic energy says it is still inside the material, it has not come out. So for this one, the negative kinetic energy is more, that means more energy is required to remove it. Now we will go to another important graph, that is photoelectric current. I will rub this. So you have to remember these points. Photoelectric current versus stopping potential. That is more beautiful now. If you have followed photoelectric effect, you can understand this. I will draw a graph of photoelectric current versus stopping potential. We'll have to draw the graph now. Photoelectric current versus stopping potential. Yes. Right. Now, 1 minute. Okay, stopping potential is made positive. Yes, correct. Now, I will take a suitable high frequency radiation to fall on the surface for a frequency which is much greater than nu naught. What do you mean by that? I have used sufficiently high energetic photon to fall on it. That means outcoming electrons can come out easily and they have some remaining energy that is in the form of kinetic energy. Your father has given you enough amount of money, that means some 150 rupees. You have 70 rupees for traveling and you will have 80 rupees remaining and you can spend it as you want. So nu is greater than nu naught. What happens? Electrons will be coming out and photoelectric emission is happening, and if you increase the brightness of the light, more and more electrons will be coming out, current goes on increasing. Now what I will do is, I will make say some 100 electrons are coming out of the material and you can count them, they have enough energy. Okay, let them be coming out. Now what I will do is, I will give negative potential. I will connect it here and I will give negative potential. When negative potential is given to the anode, even though the electrons, 100 electrons are coming out with sufficient energy, they have been given more energy, so they use it, some part of the energy is used to come out and they are coming in number, but when they come here, they get surprised. That anode is made negative, we are repelled from here, and the negative potential of the anode, say it is, I will write the values, right? Say if it is 0, -1, -2, -3, I will write it in the reverse order. -4, -3, -2, -1, 0. It is in -4 volt, which is sufficient to stop the electrons. Say it is -5 itself. I have given sufficient negative potential so that it is greater than the stopping potential also. I have a person who has enough energy, more than enough energy to stop these stones falling from the hill, right? Then I don't have any problem. What is the photoelectric current now? It is 0. So stopping potential is along the x-axis. So this is -1, -2, -3, -4, -5, and this is 0, +1, +2, +3, +4. Okay, so like this I will write +5. Just for your convenience, I will write some numbers. So photoelectric effect is occurring now. I am putting sufficiently high kinetic energy photons, sufficiently high energetic radiation, and they are strong enough to remove the electrons. Electrons are coming out and those electrons are having enough energy, but when they reach the anode, anode was successful in stopping all the electrons because negative potential is given, and given is very high, and the electrons can't reach the anode. So what is the photoelectric current? Y-axis 0. Where is the stopping potential? Here. Graph is here. Am I right? Decrease it little by little, make it -4. -4 is also sufficient to stop the electrons because that itself is the stopping potential. What is the photoelectric current now? 0. Why it is 0? No photoelectric emission is occurring. Photo emission is occurring, but electrons can't reach the anode. It can't reach the anode. So 0. Make it -3 now. -3 volt. -5 to -4. -4 to -3. Now, out of all the electrons, some electrons may be successful in reaching the anode. They may reach the anode. I have already told in the previous class that in this concept, you may have some doubt. I will deal with that later, not now, because it becomes totally confusing. If you have that doubt, you keep it with you. You ask that doubt. If you have that doubt, you ask that doubt in the WhatsApp. I will narrate you, or I will give you some clues. Then you will understand. I won't explain it now. I will explain it later. If some of the electrons are reaching the anode and some of the electrons are stopped by this -3 volt, what happens? Photoelectric current will not be zero, because some electrons will be reaching the anode. So photoelectric current starts rising up in the y-axis current. Bring it to -2 volt. Again, few electrons out of 100 electrons, say 20 electrons were successful in reaching the anode for -3 volt. When you make it -2, few more electrons, some 50 electrons may be successful in reaching the anode, because stopping potential is becoming weaker and weaker. So the current goes on rising. Current goes on rising. When the stopping potential is 0 volt, that means you make it 0, many electrons will be reaching the anode. But some of the electrons may not be reaching. You make it positive. What do you mean by making this positive? Again, going back to the original case. So you were in -5 volt, -4, you are trying to stop them, successful in stopping them, but not completely successful, partially successful. Here very unsuccessful. Here electrons have started reaching the anode, and because they have energy, and the number of electrons reaching the anode goes on increasing and increasing and increasing. When I reach to +2 volt, so +1, +2 volt, this is inviting electrons now. So I am connecting it here, right? It is connected here. Now you see this one here, from here, like this. Of course, it is not connected here. Like this, it is negative, and this is positive. Now the electrons are successfully reaching the anode. Say all 100 electrons have reached the anode. All of them have reached the anode. Make it +3, +4, +5. No use, because all the electrons are coming now. Now even if you cry, come to the anode and make the current more and more, not possible, because once all the electrons reach the anode, current becomes steady. It reaches steady value. Did you understand it? Negative anode is given, or anode is made negative, cathode is made positive in order to stop the electrons. When the stopping voltage is strong enough, it was able to stop all the electrons. Photoelectric current collapsed to 0. But when the stopping potential is made weaker and weaker, -4, -2, -1, some of the electrons will be successful in reaching the anode. That gave you the photoelectric current. So current has started rising. When the number of electrons reaching the anode become more and more, as the negative potential is made positive and positive and positive, more and more electrons will reach the anode. But there is a saturation. Suppose 100 electrons are emitted from this radiation, and these out of 100 electrons, initially 10 electrons will reach, next 50 electrons will reach. When all the electrons reach, by the time you reach say +3 volt, there is no question of inviting few more electrons, because emitted electrons themselves are 100. Then how come you expect more electrons here? It reaches saturation. Sir, if you want to make more electrons to come, what you have to do, sir? Increase the brightness. But we are not changing the brightness. What is this graph? This graph is current versus stopping potential. You are changing the stopping potential with respect to current, right? And getting a change in current because of change in stopping potential. Nobody has asked you to change the brightness. This is for one brightness, one intensity. Agree? For a particular intensity, this is the graph. Okay. If you change the brightness, do the same experiment. Yeah, decrease it, bring it to -4 volt. Make the brightness more. For another brightness, what happens is, when the brightness of the light is increased, when the intensity is increased, same light will be emitting the same type of photons, but number more. Just try to recollect what I have told. This is what Einstein gives the explanation, but I will tell you now only because you can follow it. So when the intensity of the light is increased, you are making the same type of photons to come out, but their number is more. If you want different types of photons to come out, change the color, wavelength, frequency. You have to change the frequency or you have to change the wavelength, then only the type of photons will change. Now you are making the same type of photons, but more in number. if same type of photons come, they will emit same energetic electrons. The energy required or the potential required to stop the electron is same. So make it minus 4 volt, make the brightness more. When the brightness is more photons will be emitted, photons will be falling on the cathode, more electrons will be coming out. Now the thing is, all those electrons will also have the same kinetic energy, so same minus 4 volt will be enough to stop them. Now try to make it weaker, stopping potential, make it weaker and weaker. Minus 5, minus 4, minus 3, minus 2. What happens? The number of electrons reaching the anode increases. Minus 1, more electrons will reach the anode. Again, the current level from here starts rising. But it will land up in a higher level. Can you tell me why? When you make it plus 2, plus 3, plus 4, plus 5, the number of electrons reaching the anode will be more, because it is not like last time. You have increased the brightness, you have increased the intensity of the source and did the same experiment again back. Now it is more intensity falling on the cathode. It will emit more electrons, more photons falling on the cathode, more electrons coming out. That produces more landing current. Suppose 200 electrons were emitted and all the 200 electrons were stopped by minus 4 volt. And it is stopped by minus 3, but not as much as minus 4. And when we come to plus, 200 electrons will reach it here. Current will be more than the previous case, so it will land up here, but stopping potential same, minus 4 volt. Now you have understood? Decrease the intensity. Decrease the intensity, not changing the frequency. Don't change the frequency. Decrease the intensity of the light. When the intensity of the light is again decreased, now what happens? Say some only 50 electrons were emitted. Then the current will be accordingly, you will have lesser current. Make the stopping potential more negative. This stopping potential can stop the 40 electrons. Now make it 50 electrons. Make it minus 3, minus 2, minus 1. Photoelectric current starts raising up, but once all the electrons reach here, again it reaches saturation. But that saturation is different because only 40 electrons are reaching. So this is intensity 1, this is intensity 2, this is intensity 3. Less intensity will land up with less current, more intensity will land up with more current, and much more intensity will land up with much more current. That's all. So a graph of intensity versus photoelectric current will be like this. Okay? Now shall I draw the same graph with different frequency? That is more interesting now. Hope you have followed this, right? Right? Now I'll draw it here. A graph of photoelectric current. I have so many wires on my body, right? So this, so I have to be very careful while turning. I have a mic. Yes. Stopping potential here and photoelectric current. A graph of stopping potential for with the photoelectric current for different frequencies now. This is minus 1, minus 2, minus 1, minus 2, minus 3, minus 4, minus 5, 0, 1, 2, 3, 4. We'll do it for different frequency. Now let me introduce a frequency, new one, which is greater than threshold frequency. Say threshold, I will write that value, that is better, right? I will rub this because this is not needed now. Say 2.1 into 10 to the power 15 hertz, no photoelectrons. 2.2 into 10 to the power 15 hertz, photoelectrons are emitted. 2.3 into 10 to the power 15 hertz, more than threshold, this is threshold, emitted. 2.4 into 10 to the power 15 hertz, definitely emitted, definitely emitted. So any frequency greater than threshold frequency is enough to remove the electrons. Now I am at 2.5 into 10 to the power 15 hertz, say. What happens? That means, I will compare it with the money that is given by your father to you. Say your father has given, where is the threshold frequency here? 70 rupees. That means you have just enough money to go. And your father has given 100 rupees. Your father has given 150 rupees. Your father has given 200 rupees. Say, simply comparing it with. When your father gives the enough frequency, enough money, you are left with the only 0 money, 0 rupees. So this is kinetic energy of photoelectrons. And when your father, now I have to draw the graph here, isn't it? When your father gives 100 rupees, your left money is 70 rupees for traveling, so 30 rupees, 80 rupees left with, and 130 rupees left with, right? So you'll have more and more money left with. That means your kinetic energy will go on increasing. Since you have more money with you, as soon as you get down from the bus, you will run with such an enthusiasm towards your grandma, because you have more money with you, right? So you are happy indirectly that you have more money in your pocket, so that you can buy something else and you can enjoy. So for stopping potential, minus 1, minus 2, minus 3, minus 4, and minus 5. And here 1, 2, 3, 4 volt, and this is a photoelectric current. A graph of photoelectric current versus stopping potential. Okay? With the different frequencies. This is with different intensity, brightness. More brightness gives more current when you are coming to positive potential. Now let us have a frequency, this one, 2.3 in 10 to the power 15 hertz. What happens? Even if this frequency is greater than threshold frequency, even if the photoelectrons are emitted from the surface, they can't reach this one, because I am at negative potential. I am at stopping potential now, say minus 4 volt. Okay, you just try to change the stopping potential, decrease it, minus 3, minus 2, minus 1. Then the electrons will start reaching the anode, and you will get a photoelectric current, and the curve comes like this. Correct? Now this is the first curve when the frequency is this one. Now you just come to the track, frequency increased. If you are given 100 rupees, grandma has to be ready with sufficient energy to greet you, because you will be running with some 30 rupees of money and you will be happy, and she will stop you. Suppose your father has given 150 rupees, if the frequency has increased, you will have 80 rupees with you, and you are more happy, and you will run with the more energy, and grandma has to be ready with more amount of energy to stop you, isn't it? These electrons were less energetic, these electrons are more energetic. When radiation of higher frequency is made to fall on the cathode, more energetic electrons will come, because they will also spend the same amount of energy to come out, but they will have more remaining energy, so they will come faster. What about the stopping potential needed? Stopping potential needed will not be minus 4 volt, it should be minus 5 volt, isn't it? Because they are having more energy. So here there will be some current, because minus 4 volt may not be able to stop the electrons, as these electrons were stopped. Electrons stopped when this radiation was incident, were having lesser energy, because only this much. When the frequency was increased, those electrons were having more energy, you need more stopping potential. The previous stopping potential may not be able to stop them, so there will be some current. So only for minus 5 volt, the electrons will stop. What about minus 3? It cannot stop. Minus 2 cannot stop all the electrons. So, but what about this landing? It is same. See the graph? Sir, why did you land it here only? Because current is same. Why? You have changed the frequency. You have not changed the intensity, brightness, because brightness decides current. You have not changed brightness. Same brightness, different frequency. Hope you are following. So the same intensity light, but with different frequency is incident. You get same number of electrons, but they are energetic. So more stopping potential is needed to stop all those electrons. But when the stopping potential is weak, you get more and more current. But you can't have more current than the previous one, because you have not changed intensity. Still increase the incident frequency. When the incident frequency is much more, again much more stopping potential, say minus 6 volt is needed, but landing position is this one only, here. So while looking at this graph itself, you must be able to explain which one graph explains what type of criteria. That is very, very important. So if a graph of, so I don't show this one, just I draw the graph, and you must be able to put it in a proper way, right? I'll take a new chalk piece. Okay, it's not available. Yes. Stopping potential versus photoelectric current. Stopping potential versus photoelectric current. Okay. A graph like this, a graph like this, a graph like this. A graph like this, a graph like this, and a graph like this. What is the difference? All the graphs are landing in the same current. What do you mean by that? Intensity same. Same intensity of incident radiation. For intensity of incident radiation is same, but different stopping potential, right? Different stopping potential. What do you mean by that? Different kinetic energy for the photoelectrons, because you need different energy to stop them. Different kinetic energy means I call this graph as 1, 2, 3. Then kinetic energy 1 must be much greater than kinetic energy of 2 must be greater than kinetic energy of 3, because 1 needs more stopping potential, say -1, -2, -3. It needs -3 volt to stop. That means those electrons were more kinetic, more energetic. This -2 volt is stopped to stop them. Less energetic, much less energetic. What about the curves here? This curve is very important. This curve here, you see, all are ending in the same stopping potential. Same stopping potential means same kinetic energy electrons. Then what did you change? We didn't change the frequency here. Frequency is not changed. So frequency same. All frequencies are same. Then what is different? Current is different, right? Current different means this is more brightness, this is less brightness, this is least brightness. So intensity of the first radiation must be much more than the intensity of the second radiation, and then the intensity of the third radiation. This is what you want to conclude, and this is very important part in this. We will recap it again in the next class, and we will see how it is so, and you will be asked to explain this. So in the next class, I think by the end of the next class, I will be not dictating, I will be showing you what type of questions will be asked in this and how to write the answers. I think almost we have come to an end, but I have still some 15 to 20 minutes of discussion on this, so this should be very clear. Try to read this. I will send you the notes. Try to read them and make them very clear, so that you can answer to the question. Sometimes people will know everything, but they don't know which answer has to be written for which question. So don't have such confusions. Try to read them properly. I will give you question and answers. See them. For any doubts, you just ask in the WhatsApp. I will answer it. So thanks for watching the class. We will meet in the next class with few more discussion, and we will finish it up, and we will work out some problems in this. One single formula, Einstein's explanation, and that you can follow easily, and then problems. So we will meet in the next class. Thanks for watching. Thank you.